Okay, this is the last session, and I took a photo so that I know who you are. And when you come for funding, I will take note of you. I'm joking. Okay, this is serious matter. I'm going to talk about the strategy, so I leave all the jokes to Marcus later. Okay, first I must congratulate Create for the 10th anniversary that you have done. Great job after these 10 years. But today I'll be just covering on the section on energy system, giving an overview of how we do R&D using an integrative approach towards achieving a coherent energy ecosystem. Okay, these are the driving forces for energy. I mean, energy, land, water, and they're all what we call scarce resources in Singapore. So you need to compete. I mean, we have to compete if you want to look for investment in energy. You need to compete with space, land, and livability, and you know that also as far as we import almost all our energy. 95% of our electricity actually come from natural gas. So very limited option to tap on renewables. There's no wind. It's only 3 meters per second. You cannot do anything with 3 meters per second unless we can have you research and come up with a turbine that can do efficient energy conversion at that rate. No tidal, no geothermal. So we rely a lot on solar. And maybe in the long time, in the long future, nuclear energy. Okay, this is also the driving forces. You notice that my slides and Patrick are quite similar because we are so aligned. We agree with each other so well that we share the same slide. So we need to address the energy trilemma, looking at energy security, making sure that energy is affordable and at the same time sustainable. So there's lots of emphasis on renewable and clean energies. So energy is an integral part of urban solution and sustainability. That's what I'm responsible for. And you notice that before RIE 2020, energy, water, and land were actually run separately, independently. And we realized that actually there's a lot of synergy to put them together and fold them in the urban solution and sustainability to leverage the synergies of energy, water, and land and livability to deliver integrated solution so that you can meet our national needs and also to be able to create economic value. We spoke to many of our industry out there, and they think that actually it makes a lot more sense if we develop integrated solution, and with integrated solution, it leverage the emerging capability of the system and be able to sell better and create economic value. So this is a snapshot of the investment in energy since 2006. And you notice that in the past, in S&T 2010 and S&T 2015, there's been quite a lot of focus on developing component technology. So we look at how you develop PV, storage, and demand management. You look at how to make energy more efficient in buildings. And it is in RI 2020 when we look at when we put the three together, we think that we need to focus on pulling all the components technology together to develop for system integration, to develop system level solution, and also for industry alignment. And therefore, there's also a lot of emphasis to look at how we can have the full chain from the basic research all the way focusing on all the different, to make sure that we have all the players in the ecosystem, from R&D, basic R&D, applied R&D, to industry-oriented R&D, and also to make sure that there are technology adopters to adopt our impactful R&D outcome for commercialization. So, working together to realize Singapore energy vision, we work to make sure that we have a good ecosystem, to make sure that we can balance supply and demand, and at the same time, to make sure that we maintain a world-class system grid. I mean, our SAIDI, SAIFI is still very good, so we want to maintain that as we continue to load our grid with renewables and other form of distributed energy sources. We want to make sure that we continue to maintain grid stability. So these are some of the technology, component technology that we have developed. And we think that these are all the technologies. I mean, it's not all. I mean, these are technology that we have developed, and then it now make a lot of sense for us to put them together and develop integrated solution. So we came up with a system level integration whereby we want to see how we can integrate all this into a system level solution to make sure that then this system will actually have capability greater than the sum of individual parts. So first of all, central to this is the intelligence. We want to make sure that you develop an intelligence network to be able to monitor the system for real-time monitoring, for isolation, and also to make sure that the system perform at the right time, right reliability level. So the intelligence part is important. The smart grid part is important. That this actually is a key to the grid of the future, where we call it Grid 2.0. Then distributed energy sources. This will continue to, we know that it will continue to be added to the grid. PV integration that will help to load more clean energy onto the grid, and this will also help to then reduce the carbon footprint. And also, we know that because of the intermittency or the variability of solar power, there's a need to make sure that you have storage to buffer the variability of solar energy. But we know that at this moment, the storage is still expensive, so we are relying on you to deliver more cost-effective solution. But so in the meantime, we think that it's good to develop solar irradiance forecasting, so that if I can forecast half an hour ahead of time for an impending cloud cover, then I would be able to give me time to power up my spinning reserve. Would to some extent, if it's more cost effective, then I do that rather than invest in power to power the equal amount of storage energy. So I would just invest on enough storage energy to cater for the rapid fluctuation. Anything that actually I can forecast, I can look at other alternatives. But in the long run, if storage cost comes down, then I think we will be able to use storage more effectively. And waste heat, harnessing waste heat is important. That I think that there is a lot of opportunities to harness even low-grade heat. Heat that are generated from industry, if they are thrown out into the atmosphere, they heat up the environment. So there is a lot of opportunity for us to harness this waste heat to generate. There are many uses for it. I mean, we have cases where people harness heat just for hot water, for example. So, I mean, instead of throwing the waste heat out and heat up the environment, you harness it for good use. And also cold energy, for example. Cold energy, if I can harness cold energy, I can use it for cooling, refrigeration. I can even use it to drive piston for cold energy vehicle. For example, if I have LNG that is at minus 165 degrees, if I can store it into compressed air, liquid air, at the same atmosphere, when this get gasified, is 700 times expansion. That could actually help to, even you can drive piston, and if you have cars that actually work on cold energy, it cools the environment too. So these are all the side effects of it, the positive side effects that we are looking at. District cooling, we think, in fact, SB Power told me that when they implement district cooling for the Marina Bay, one marina, they said that they save 10% of the energy. So I tell them that probably you can save more if you use phase change material. I think if I use phase change material as a cooling medium, I can actually increase efficiency of district cooling more. I mean, instead of having ice that freeze at 0 degrees, if I can have phase change material that change phase at 8 degrees, for a factor of 3% per degrees change, the chiller efficiency can actually increase by about 25%. So this is the kind of research that I would challenge you to look at if we can develop more cost-effective phase change material. Then, focusing on the demand side, I think if I have good monitoring, I monitor energy envelope of building envelope, forecast occupancy rate, I can adjust airflow for thermal comfort. To a large extent, I will use less energy, and that would also help in the energy efficiency and also reduce the carbon footprint. AC to DC, if I don't have to do AC to DC conversion all the time, I will save about 14% of the energy without having to do all the multiple conversion. Demand response will always allow consumer to put some of their non-critical load for peak load shaving and also to help to manage our supply. So we are looking at any kind of unconventional load that's possible. Right now, I think the industry for demand response, probably we only have about 72 megawatt of power for demand response. You look around, we are looking at our telco-based station. There are 10,000 telco-based stations in Singapore, each with 5 kilowatts and 5 hours of backup. So you see them, you put them all together, there are 50 megawatts of additional interruptible loads that you can leverage. So these are examples of interruptible loads that you can look at to manage your power, your demand. And last but not least, solid-state transformer. We think solid-state transformer will be the game changer to look at how we can improve power quality, have a smaller footprint, and also grid resilience. So these are some of the opportunity that I'd like to share with you, that if there are good ideas on this, we'll be happy to hear from you. And then I think this is how I envision the Grid 2.0 architecture to be. In order to make sure that there is interoperability by design, it is always important to look at the architecture. So this Grid 2.0, we see that as a two-tier architecture comprising a physical mesh network of microgrid for grid resilience. And this is overlaid with a comms network for intelligent system monitoring and control. So I would like to acknowledge the contribution by CREATE. It's 10 years. I think you have done a lot. I think most of the work has been very useful to us. I'd like to congratulate you for the outstanding R&D outcome that you bring to energy sustainability. And I will let you hear from the rest who will talk about the detail of what they have done. But I know together we will deliver good R&D outcome that can be integrated in system-level solution, and for us to facilitate our translation to commercialization and to meet our national needs. And with this, I thank you.
Great, thank you very much, Dr. Yeo. We'd now like to invite up Professor Marcus Kraft of CARES, otherwise known as Cambridge Center for Advanced Research and Education in Singapore, to address how CREATE's research responds to the energy challenges set forth in Dr. Yeo's talk. Professor Kraft is a fellow of Churchill College, Cambridge, and professor in the Department of Chemical Engineering and Biotechnology. Professor Kraft has a strong interest in the area of computational modeling, with emphasis on carbon emissions reduction technologies for the automotive, power, and chemical industries. Looking forward to your talk.
mic. Yeah, that would be good. So hello everyone, I'm glad to still see you here. Okay, I'm the last but one. Okay, and as you may have guessed, this is about energy. Okay, so it's not just about energy, it's about energy research at CREATE. You know who I am. CARES has just been introduced, and we have one program that's called Cambridge Center for Carbon Reduction in Chemical Technology. Right, okay. Just a summary of what we've learned so far, okay. We know that CREATE programs do research in the energy area, and they all address, as we've just heard twice today, that there is a trilemma, okay. And we all address the Singapore's energy trilemma, and in particular, and this is in particular true for our program, to address this trilemma and reduce the carbon dioxide emissions. Okay, we are different, there is a collaboration between Singapore universities and the CREATE entities, and I will tell you in a minute what they are. Okay, so this is an attempt to give you an overview of what energy research is done at CREATE. These are the individual institutions, so this is us, Cambridge, ETH Zurich, MIT, Berkeley, Chiao Tong University, TU München, and Hebrew University. So you can see here, that's the energy trilemma. So energy affordability, energy security, and energy sustainability. And this morning, you've seen a variety of activities in the CREATE program, and they cover different areas in this trilemma. So I have subdivided affordability, which could also be efficiency, into equipment, building, industrial park, and city. Energy security, I've just left undivided, and energy sustainability, solar harvest, and electronic transport. Now you see here there are some red circles, and I will not talk about the energy activities in these circles because there will be speakers who will do this for me. I will just give a short overview on some of the other activities. So let's start with B1. Okay, so let's first just recap what we've heard this morning from ETH Zurich program. So this is the Future Cities Laboratory, and here energy plays a role in terms of how can we build new buildings more energy efficiently. Okay, and what you see here is one of the key projects that ETH had. So this is the 3-4-2 concept. Here you want to realize savings in operational and material cost. And you do that by basically redesigning the interior, get more space, change the way cooling is implemented, use water instead of air, and have some small decentralized ventilation units. Can you go back? Okay, so D1. Okay, so again, this is Future Cities Laboratories. Here, we're not looking at energy savings on a building level, but at city scale. Okay, so the idea is to look for integration strategies to increase the energy efficiency of building stock. So that means several buildings next to one another. Identify spatial synergies. How to place these buildings. This can be possibly the local weather. It can be the vegetation. And then translate these findings into planning recommendation. I think one of the key products is this City Energy Analyst tool that allows you to do exactly that. Can we go back? Right, okay, so now E1, so I go row by row. So this is now again Zurich, but that's the Future Resilient Systems. And here we want to make sure that the energy supply is resilient to disturbances. Okay, and why is that necessary? Okay, here are a few points that may lead to a high risk with respect to making the supply steady. So you could have aging infrastructure, lack of support tools, increased system complexity, lack of personal training. So it's not just technical factors, it's also human factors, loss of system observability. That's important because the observability is closely connected to control, and loss of relay dependability or security. So here the key tool is risk monitoring, detection, and control. So how do you have to design your system so that it doesn't collapse if few components cease to exist? And that is closely related to robust optimization. Can we go back? Okay, so what's next? So let's do D2. Okay, this is the E2. S2 program, we've heard before, they deal with coupled problems in future cities, in basically how can we live better and more sustainable in a future city. And there is a variety of problems that are addressed. One that I just want to highlight that was mentioned already was the waste management in megacities. And of course, with the waste management, there is a chance of energy recovery. There was an example of the integrated anaerobic digestion and gasification of food wastes. Okay, here you see an example of such waste. This could be either a processed sludge or it could be manure. So there are different food wastes come in different forms. So once you have it like that, you can then put it into a big fluidized bed, a gasifier. With the gas, you may get syngas, and that, of course, can then be used for further either chemical processing or combustion. So in other words, this gives us additional value out of our wastes and, of course, helps to reduce the amount of energy we have to import. Can you go back? Okay, so I now want to have G1. Right, so this is also some content that we have seen today, but it also fits into the energy domain, so that's why I've chosen to talk about it. Transport consumes quite a lot of energy. Here, the TUM program, the Technical University of München, they want to basically create a public transport system which integrates with the backbone of the MIT. We saw earlier these chains of little trams, okay? So they were all electric. So what is necessary, or what happens in this program, that on the one hand, they design a sort of a technology platform, a design of an individual vehicle, and that includes battery placement. Of course, then the question is, where does the electricity come from in order to charge its battery, and what does that mean to the power grid? And for that, they investigate the overall infrastructure, create a smart charging system, and try to understand how that influences the choice of power stations. Okay, can you go back? Right, so at this stage, I would like to stop. I think I have given every institution some credit because we all work in the big energy realm. And I would like now to, hang on, next, to introduce to the following speakers. So there will be somebody from Bayer Synberise, that's Nirpan Matthews. He will talk on photovoltaic. So then Meiji, my colleague from CARES, will talk about carbon footprint reduction in potential in Singapore. Shlomo will talk about manufacturing materials, manufacturing of advanced materials, and Eugene will talk about integrated circuits. Right, so Nirpan, are you here? Ah, yeah, great.
Good evening, everyone. I think this might be the most detailed presentation you will see today. So I come from Symposium. So we are not as old as 10 years. We are turning 5 in March. So this is the second program under the Berkeley Research Initiative, and these are the folks involved in the research and collaborators. Today, I shall be talking specifically about perovskite photovoltaics. But before that, so Symposium, the driving message behind Symposium is that we want to make breakthrough translational technologies for sustainable energies. That means so the research activities in Symposium actually go from TRL level 1 all the way to about TRL level 6, 7. There are 3 thrusts within Symposium. One is related to making highly efficient perovskite solar cells. Some directly attack the solar to fuel conversion, which is an extremely difficult problem, and looking at new catalysts for carbon dioxide reduction. And the third thrust tries to scale up all these areas into translational products which could be employed in demonstrations and products. So I shall be talking about the perovskite solar cell efforts in thrust 1 and thrust 3 in this talk. So just to briefly set the stage. So when photovoltaic research is typically done, the logic is that you either need to make it very, very cheap, or you need to improve the efficiencies. So a lot of areas of research in solar cells exist primarily because the logic is that you can make things very, very cheap, and that would revolutionize things. However, the problem is that even if you make things extremely cheap, you still cannot actually implement things. So even if you have a module price which is almost zero, you still need to have a reasonable efficiency so that your energy cost is controlled. And that is because if your efficiencies are too low, you need to install too much of the solar cell, the support systems will still cost as much, and therefore you definitely need to have high efficiencies to make it logical. So even if your solar cells are very fancy, they can be printed, they are flexible, whatever, they're transparent, you still need to get high efficiencies. Without that, you are dead in the water. But you can still publish papers, of course. I can say that, I'm a professor, so I can say that. So perovskite solar cells is relatively new. So effort in perovskite solar cells started about in 2013, 2014, and you can see that the efficiencies of these devices have already outstripped the other conventional third generation photovoltaics. So like amorphous organic photovoltaics, dye-sensitized solar cells, the efficiencies of these devices are much lower than that of perovskite solar cells. And that is not because of the researchers working on this, but because the material system is extremely robust. It has a fault-tolerant property that allows you to fabricate these devices with high efficiencies. Of course, my silicon colleagues would argue that these efficiencies are noted in very small devices, and they're completely correct. So there is still a way to go, but the research activity started off only in 2014. So in terms of defect state densities, etc., these perovskite devices have very low defect densities, reminiscent of systems grown through high vacuum processes. However, we process them from solution. So we can get high quality properties, including high power conversion efficiencies, optical absorption is very good, excellent electronic properties, all while depositing from a solution. And of course, it need not look black. We can change the color very easily as well. Because of all these applications, and of course because of the fact that the efficiency is very high, perovskites are very heavily researched. And perovskites are also compatible with existing silicon-based solar cells, and I'll be talking more about that in detail in 1 or 2 of the slides later. So in Symposium, almost started at the same time perovskite solar cells were being researched. So we actually were just in time and fortunately placed to do some of the seminal work in terms of measuring the charge transport properties, demonstrating band gap tuning, discovery of lasing, making newer types of halide systems, using it for a wide variety of applications, even making nanoparticles which show hot carrier devices, etc. But this set aside, we have been tackling both fundamental and technological problems within halide perovskite systems. And right now, we have focused more on 2 specific areas. So in terms of fundamental questions, we look at how you could improve the stability of these systems, how would you use the same logic to design new halide semiconductors for areas even beyond photovoltaics, And of course, in terms of technological opportunities, how would you employ perovskites with existing solar cell technologies, thus allowing it to go to market much faster, as well as how to make these things very, very big. And then this would justify what Fritz does for his day job. His day job is not to click the video. His job is to make perovskite solar cells. So I'll show that later. So in terms of, so these two features highlighted in green is what I'm going to focus on. So the first the first project is something we work hand in hand with UC Berkeley through the Symposium project, where there is perfect complementarity in the two groups. So Matt Sherburne and Mark Asta work on high throughput computational screening of newer types of halide semiconductors, while we are the experimentalists which make these materials, make devices out of these, etc. So this is an example of the different variety of semiconducting materials you could make using the same logic as that of the existing perovskites. And then through a high throughput computational screening, you can look at the different combinations possible. You can see which one of them will absorb enough light, which one of them will be stable, which one of them will have reasonable charge transport properties. And based on that, you can actually narrow it down to a couple of material systems that you could fabricate. And we are in charge of making these devices. So it's a very nice cooperative partnership in terms of looking at newer types of halide perovskite semiconductors. The other area that we focus on in Symposium is, as Dr. Leong Weng showed us, Singapore has a problem. Singapore needs to have energy at multiple locations. So what Singapore has is high-rise buildings, and therefore you could talk about other ways of integrating solar cells into the scaffold. And that is where we are trying to make perovskite solar cells that can be integrated onto windows. So this is the kind of configuration of the solar cells that we fabricate. The key factor to remember is all these layers are actually printed by us. So we use the same process as we use for making screen printing process, as the screen printing process that is used for patterning designs on top of a T-shirt. We use the same kind of process for fabricating these solar cells. So these are the different layers that we put down. And because of this carbon layer, they are much more hydrophobic and more stable. So starting off with a very low efficiency of about 2%, we went to 70 cm squared. We went now close to 30 cm by 30 cm squared devices. And many of the processes that we utilize are using printing processes. So this is an example of a slot die coating process, whereby which, in this case, because of the fact that we use very low temperatures, you can print it on top of plastic. And then we dry out the solvent at about 100, 120 degrees centigrade to form the film. So starting at our 2% efficiency, because we are looking at a completely printed process to begin with, we've gone to 70 cm squared. Now we've gone to larger areas. So this shows you that slowly the material is crystallizing when you start to anneal. And then you can hold it up to the window. So you can directly, let's say you have a see-through window, or you could have, well, these are very closely spaced lines, but you could space them apart to have more visibility. So based on this, now we have scaled it up to 30 cm by 30 cm, and now we are in the process of working with companies in integrating them into Windows, et cetera, as well. So in Symposium, so just to conclude, in Symposium, we have worked extensively on understanding this material system, which is very, very novel and very, very new. So because of that, we have had to look at quite fundamental properties, but also look at technological translation of these systems, how we could do this. So specifically, these large area solar cells, what we have shown now, the 30 cm by 30 cm is the largest module that has been ever made of these devices, and that is just next door. So we are trying to solve these problems and try and improve the efficiencies of these devices such that they can be either integrated with existing solar cells, or they could be a viable building integrated photovoltaic. Thank you.
I think I'd like to ask Meiji Lim on the stage. She will talk about carbon footprint reduction potential in Singapore. Meiji.
Distinguished guests, ladies and gentlemen, it's my pleasure to be here today with you at Create at 10 Symposium. I'm Meiji and is representing Cambridge CARES. So today I would like to present to you the carbon footprint reduction potential in our C40 program, which is the first interdisciplinary research project administered by CARES. So, C4T stands for Cambridge Centre for Carbon Reduction in Chemical Technology. It's actually being set up to investigate and develop technologies to reduce carbon footprint of Singapore's chemical industry. The energy and chemical industry has been a mainstay of Singapore's economy since pre-independence days. Over the years, Singapore has developed an extensive chemical value chain that is heavily supported by innovation and research. Today, Singapore is the world's 5th largest refinery hub and ranks top 10 globally in terms of chemical export volumes. And as we know, in the energy and chemical industry, combustion plays a significant role. Combustion is also the overwhelming contributors to Singapore's CO2 emission in year 2012. So, as you have may known, in the Paris Agreement on Climate Change, our C40 program is actually structured to look into this significant area. We actually propose 3 routes to reduce the carbon footprint in Singapore while simultaneously supporting economic growth. The 3 routes that we propose are 1, cleaner fuels, 2, capture, utilization, or avoidance, and 3, improve efficiency. The C40 program is then further structured into 4 different interdisciplinary research projects, or IRPs. So, IRP1 looks at capture, utilize, and avoidance by investigating low-carbon reaction engineering, which includes CO2 capture strategy from flue gas, and more efficient catalytic and separation processes. An example is chemical looping, which I'll be talking about in more details later. IRP2 looks at cleaner fuels by developing novel electrochemical technologies to exploit low-carbon electricity sources such as renewables, solar renewables. IRP3 looks at both cleaner energies and improving efficiency by 1, identifying fuels and fuel mixtures for low-emission energy conversion, 2, more efficient catalytic and separation processes, and 3, reusing waste resources. So, 2 examples, more novel efficient hydrothermal treatment process and J-Park simulator will be covered in more details later. And the last IRP, IRP4, looks also at improving efficiency by examining how CO2 emission associated with electrical supply to chemical industrial parks such as Jurong Island can be minimized. So, in this slide, the overview of the carbon footprint reduction potential of our C40 program is illustrated. The technologies have been classified according to the 3 proposed routes mentioned earlier. So, for example, under capture and utilization, chemical looping and vapor sweep adsorption have been listed. But do note that some of the options in this figure are not additive. So, for example, if solar PV is used to supplement the electricity grid, the same amount of energy cannot be used to produce renewable hydrogen. So, after excluding such cases, the total CO2 reduction potential of the technologies investigated by our C40 program is approximately 8 million tons per year. And this is approximately 18% of Singapore's year 2012 CO2 emission. So, going forward in the next few slides, I'll be talking in more details about 3 selected technologies. The first technology that I'm going to talk about is actually improving efficiency for sewage treatment. So you might have known that in Singapore, sewage can be used to generate electricity. In a conventional process, sewage is first digested to form biogas and sludge. The biogas is then incinerated to produce heat, which can be used for electricity generation. On the other hand, the sludge is then dried using an energy-intensive thermal drying process to produce dry sludge. The dry sludge can then be either sent for incineration to produce even more heat or be sent to the landfill. So, our C40 program has actually successfully developed a novel hydrothermal treatment process to convert sewage sludge into hydrochar, which can be used as a solid fuel. And it has been demonstrated that this new process utilizes only approximately 50% of what is the energy required by a conventional thermal drying process. So to give you an idea, if all of Singapore's sewage sludge is treated using this new process as opposed to the conventional method, it will translate to approximately 20 kilotons of potential CO2 savings per year, based on 2014 statistics. So, a startup company by the name of Go Catalyst has also been created to commercialize this process. Okay, going on, I'll go on to the next technology, which is an alternative way to combust fuel. So, chemical looping can actually be used for inherent carbon capture in fuel combustion, and this can be done via a two-step cyclic non-mixing process. So in the first reduction step, fuel is combusted in the presence of a solid oxygen carrier to produce heat and CO2. So, and the heat can be used for electricity generation. And in the second oxidation step, the solid oxygen carrier is actually regenerated in air. So this process allows your fuel to be combusted in the absence of nitrogen and trace gases that are commonly found in huge quantity in air. So as a result, the flue gas is mainly composed of only CO2 and water, hence allowing CO2 to be easily separated out for further usage. And this thus avoids the energy penalty associated with post-combustion capture. So in this scheme, as you might have realized, the most important component is actually the oxygen carrier. And C4T has actually successfully developed high-performance solid oxygen carrier with improved oxygen transfer capacity, reactivity, and redox stability. Again, to give you an idea, in 2012, Singapore's CO2 emissions associated with electricity generation is approximately 20 million tons per year. So, by assuming a 90% capture efficiency, a mere 10% change in Singapore's electricity generation by chemical looping combustion will result in approximately 1.8 million tons of CO2 being captured. And this captured CO2 can be potentially used as a chemical feedstock. Okay. The last technology that I'm going to talk about is the JPark simulator. JPark simulator is a cross-domain data storage and that is coupled with ontology modeling system that can be used for the design, analysis, and optimization of eco-industrial parks. An eco-industrial park is a cluster of business located in close proximity that collaborates with each other and the local community in order to efficiently share resources and reduce waste. So within such typical eco-industrial park, normally symbiosis relations exist not only within single network, but also among different types of network and even cross-domain boundaries. As such, it is important in order to reach a symbiotic relations amongst different industries, it is crucial to actually take into account considerations of all resources simultaneously. And this is exactly the idea behind the JPark simulator. So again, to give you an idea, it has been estimated that typical process integration studies identify potential energy savings by approximately 10%. And using the Carnegie Mellon model, it was estimated that Singapore's Jurong Island CO2 emission in year 2012 was approximately 29 million tons. So this translates to approximately 2.9 million tons of potential CO2 savings for JPark-related process integration studies. So, okay. With this slide, I would like to end my presentation on the carbon footprint reduction potential in our C4T program. We are actually coming to the end of our phase 1 program next year, and we are in the process of proposing for our phase 2 program. So we hope to build upon the successes that we have achieved in our phase 1 program and continue to actively engage with our stakeholders, which includes government agencies, policymakers, academics, and industrial collaborations. So last but not least, we'll definitely continue to positively contribute to Singapore's ratification of the Paris Agreement on climate change. Thank you for your attention, and with that, I'll pass over back to Marcus to invite the next speaker on slide.
Thank you, Meiji. Shlomo, I think stage is yours.
I think that first I'll take a photo of you in case I need money. Okay, I know that at this hour it's a little late, and I think that the best way to wake up is to show you a lot of chemical equations. So, I would like to present, not in a very scientific way, the research activities that we do in our CREATE program. This is new. This is under SHARE, which is a collaboration between Hebrew University and NTU. The program is led by me and by Professor Puisi Lee. So our program really addresses the RIE 2020 in that we have advanced materials, manufacturing engineering, and also urban solution and sustainability. What we are trying to do is to develop novel materials and devices which are related to energy and energy-water nexus, to facilitate revolutionary energy and energy-water nexus technology based on innovative manufacturing process. This includes additive manufacturing, 3D printing, 4D printing, 2D printing, and functional coding. And not less important than scientific activities, we also aim at establishing economical and industrial impact. The research activities are divided into 3 teams. One is printable energy materials, processes, and devices. The second one is energy modulation and storage system for buildings. And the third one is processes related to energy-water nexus. The common denominator is developing of platform technologies for utilization of nanomaterials to create the required devices which are related to energy, and I will give you a few examples in a minute. We also look at this line, and we have quite a successful background in this field, so I'll show you some of what we've done in this direction. Specifically, something that I'm very proud of is that the project is composed of about 10 sub-projects. Each are led by 2 researchers, one from NTU, one from HUGI. This is reflected also by joint publication, joint patent applications, and it is divided into printable materials and devices, building activities, and energy-water nexus. I just want to give you an idea about, we are now in the sixth year of our program. In the first program, we had quite many very good publications and about 50 joint papers. We were able to have quite a lot of patents. Some of them are in discussions with companies. Some already led to establishing 2 spin-off companies. And if all is okay, next week we're going to have a licensed technology to a local Singaporean company and hopefully establishing a subsidiary of this company in the field of nanomaterials for electronics. In phase 2, which started less than a year ago, we already have quite nice publications and also several patents. We also attracted money from industry, which indicates that we are already doing the research which has a real relevance to industry. So I will just give several examples of activities that we are doing in our project. Dr. Yo mentioned PCMs. So we have activity on PCM, project done by Professor Lev, which is making a new use of encapsulation method of organic and inorganic hybrid capsules. So just to give you some more examples of activities related to energy, this is in smart windows. And here we have 2 activities. One is electrochromic windows, and the other one is thermochromic windows. The electrochromic windows is a window that you press a button, and due to electrochemical reaction, it changes its appearance, its color, it can block the light. So any of you who take the Dreamliner and flew, you notice that there is no shades on the windows. You just press a button and it becomes bluish or completely blocks the light. This is done today by quite complicated technology, quite expensive, and what we're doing here is we develop both the materials and a printing technology that is already going to work with the large format printing with a local Singaporean company, so it can be done by simple process, and of course this will cause energy saving related to air conditioning. The other field, this is based on self-assembly of material, formation of transparent electrodes. I will not go into details here. And the other activity is in thermochromic windows. Imagine that you have a window that is covered by a thin layer, printed layer of material, that when it hits up to a certain temperature, then it starts blocking the infrared radiation. This is thermochromic windows. So we are working on both materials and deposition methods that you can make thermochromic windows that will still be transparent while you have a high efficiency of blocking the infrared radiation. We also have activity in transparent solar cells. There are several research approaches that are testing in our program. Here, what you see is printing of materials for making a solar cell, but due to self-assembly, this material is aligned at very thin layers that are invisible to the eye. So we were able to make semi-transparent solar cells, and we are working now on improving that. We're also working with an Australian company, hopefully that we'll be able to license the technology. We also use 3D printing, 2D printing of conducting materials, on materials for supercapacitors, materials for charging batteries. And I think that I will end up here. And just to say that I showed several of the activities that we have in our program. Hopefully, besides scientific papers, some will lead to real energy saving and establishing some more companies. We are only at the beginning in this field. And I would like to thank the CREATE organization and the NRF for the great opportunity to have Israeli scientists working here closely with local NTU scientists. And I believe that at the interface, this is the best way to get real exciting and interesting invention, and it's really happening here. We complement the expertise of the researchers, each other, and it works. So thanks the NRF, the CREATE, and you for your audience.
So thank you very much. I now like to ask Eugene Fitzgerald from SMART to tell us about integrated circuits.
Yes.
Okay, thank you.
Well, thanks very much. LEE stands for Low Energy Electronic Systems, and I am the last speaker, and I see lots of low energy out there. So I'm going to try to tell you at a high level what we're doing. I think one of the things I love about LEE is it gave us an opportunity to organize people not only around an important area in energy, but also to have faculty here and at MIT work in a new innovation model to try to produce lasting value in Singapore. So I'll talk about that. Let's see, how do I advance things? Oh, here we go. So here is one of the things that happened to us earlier in life, which is strained silicon technology, which is in every chip that you have in your phone right now. And you know, we could tell a story about how we were really smart MIT professors and at Bell Labs too, and we can predict the future, right? That's why we have R&D. We give money to people that can predict the future, right? Which means we're the best investors in the world, by the way. right? So if that were true, then I could actually, after many, many years over on the left side, figure out how to bring things to market, because of course we know how the industry is going to develop and how all the other things in the world are going to develop. And then the original market I thought about 15 years ago is still there in the exact same way, and we were able to get Intel to license and everything else. Now, of course, I'm being difficult here. People do tell stories like this, but what we wanted to do was to tell a story about a new innovation process. How does it really work? And then can we organize people around that in a very important area? And I say an important area because we've taken the electronic side, which is the consumption side of energy, for granted, actually. And to give you an idea of that, if you were to build all the electrical infrastructure today with the electrical components that we had in the 60s, you're talking about 10 to the 9th to 10 to the 10th more energy consumed, right? Of course, it wouldn't have worked that way because we don't have that much energy. So it's just that our standard of living would be drastically less. People don't realize that the important factor really is GDP per energy unit used to get the GDP, right? So how do you improve people's standard of living, but do it with very low amounts of energy consumption? And that's what the electronic side has allowed us to do, and we've taken for granted. One of the scary things is that Moore's law, which is behind all this, which is shrinking of transistors with time, with economic feedback, has stopped, which means that those gains have ceased, right? So we set out to say, let's use a new innovation model, and let's try to attack this kind of huge problem up front, and see if we can come up with ways to produce the new integrated circuits of the future that can continue to deliver a lot of GDP value, but still do it efficiently with low energy. That's what we tried to do. And so in that case, we designed the program a little bit differently. We said, well, and this actually is very consistent. I was a huge fan of Alberto's talk this morning, of course, making me realize that those of us that go through the pain of commercializing things realize what it's really like. And so we said, you know, one of the important things of this program is to start with uncertainty in the three elements of innovation, which is the market application, the technology, and implementation, which everybody forgets, but it's hugely important. Implementation is how is the industry structured, what are the business models being used? If we change the other two things, how does it get out there through the real world, right? Everybody always forgets about that piece. And I'll show you, one of the most important things we did in Smart Lease was to set up the questions for implementation in a bounded way, so innovation has to happen around that, so when we're finished, we don't have to necessarily invest in gigantic infrastructure to make a difference, right? And so here I just showed you at the beginning, the only thing we knew about the market side was that the drivers for the previous industry were not going to be our targets. This is extremely hard for people to handle because everything in our field has been driven for 50 years by microprocessors and memory. So to start a program saying, by the way, you know, those are not going to be the markets that we're going to affect. And immediately researchers go through, what are we going to do? And like, what's our target? I don't even know what we're doing. And the rest of the field says we should be working on this. You're saying we should be working on that over here. So we did know that at least, though, it's not going to be those two things, right? So, and everybody's been very excited about that, trying to find the new markets that are going to lead us to that same kind of productivity increase, but still decreasing energy as we do it. So we knew a set of technologies from people that have the interest in MIT in here, so we set that up. And then we started talking to industry and looking at what's in Singapore to see, you know, can we work with foundries that already exist so that we don't have this idea that, well, I'm going to invent something and then I'm going to invest another $5 billion to get an incremental advantage over what existed before. So these all affect each other because otherwise you couldn't have efficient progress. So, for example, you do research on technology, it decreases your options, and then that tells you, well, some of the applications we thought about aren't going to work out. And then it also means that some places we thought we're going to have to work with to commercialize things in the future, we can forget about them. We didn't have to worry about them. And so hopefully what happens over time is that you end up with multiple things on the far right side where these things come together even after you leave Create, and then we have a successful commercial enterprise. So one of the things we realized in looking at that and setting it up on the far left side was to create researchers that go through the supply chain of the industry. We could tell that it was very horizontal, so people focus on materials and processing into circuits and then in design. But of course, now those three things have to interact in order to arrive at some new innovation, right? So we put materials people, process people, device people, circuit people together, not just to independently fund all their little favorite project areas, but then to say, no, we have to influence each other. We're going to arrive at a different destination. So, you know, if you're doing a material and the circuit designer is not seeing an advantage, then maybe we should change that material or process it a different way or something like that. We're in the innovation building here in Crate, and it allowed us to build pieces of infrastructure that we could use to interface to industry and the outside world. So we could kind of move things back and forth, and that way kind of do that process I was talking about where real implementation from the beginning is involved. So here is just a list. I thought the boundary conditions set by the implementation piece of innovation ended up being the most important thing we did, I would say, at the beginning to get us to where we are today. And so we said right from the beginning, we have to interact with existing foundries, because one thing at a capital return point of view, if you said, well, whatever I build, I have to build new infrastructure for it, it turns out you can never get high financial return for that. So we knew from the beginning we're going to have to exist part of the infrastructure that's already there. We're not going to build a lot of new infrastructure, otherwise it won't work in the future. Can't get return. So we said, we got to be able to run innovation, R&D processes. Already we have a problem, which is that small processes, you have a difficult time running an industry. And you got to be able to do small batches. We got to try different technologies. We can't just pick our favorite technology. We're going to have to try different ones and see what are the circuits and then what impact do they have on the world, and then go back and change the technologies, right? So we got to be able to do that. So anyway, the exciting thing is you're really defining, as we were partway through, you can see that we're defining a new way in which we're going to build and use materials to get new integrated circuits out with different kinds of value. This is what we ended up with. I would say that it's sort of an invention of a new materials modular silicon process, where what we ended up doing is we take the front end, so those of you that aren't in the electronics area, it's kind of the high temperature process where you put all the transistors into the silicon wafer. That's the first half of making a real integrated circuit. The second half is the green part, where you interconnect all of them together. So what we realized was, you know, we got to build some infrastructure here and create, and we're going to play with this middle piece where we take the front end, we add stuff, and then we have to interconnect it back and get, for the first time, chips that people have talked about for 30, 40 years, but they've never been able to produce in a real way. And so that's what we've been able to do here in Singapore. Basically, the process looks like this, where we put a wafer into a real fab, and we put the transistors into the front end like we talked about. So this part A is done by the foundry naturally. What we do in Lee is we produce different kinds of materials on silicon, and we actually transfer this on top of here and then build the 3.5 devices in this new material underneath, and then set it up in a way that when it goes back to the foundry, it looks like it never left the foundry from this stage. So these B and C steps allow us to kind of add the innovation investment, but to leave everything else the same, and you can still get a complex system out of the foundry. This just shows you a kind of a cool cross-section where this is the thing that the industry's making in big fabs today. CMOS up here, digital circuitry. And then down here is a silicon substrate. So the way you can look at this thing, it's still a silicon technology. It's silicon at the top, it's silicon at the bottom. But what we've been able to do through a bunch of innovations invented here in Crate is we've been able to actually build a valuable 3.5 piece inside the silicon wafer that then gets processed over here somewhere, and that gets interconnected naturally in the manufacturing process. So it's a lot of material science, a lot of processing, a lot of stuff like that, but the important thing is you end up with the ability to build new kinds of circuits. And here's an example where people have dreamed of putting photonics with silicon together, and there's a whole industry called silicon photonics that has focused on the telecom part. But actually being intimate integration with light sources and detectors and all this stuff is still evasive, partly because the innovation model tells you what markets to go into, and it's not telecom. We thought at the beginning of the program this was kind of a future thing, because today silicon factories can't produce things that emit light. But what happened was, through that innovation process, it turns out this is the hottest area right now. We're being pulled faster in this direction. Again, nothing to do with microprocessors or memory, right? And so here we have a little sample circuit where these are LEDs directly integrated with CMOS, and for the first time you have circuits that can control this, all coming out of a silicon fab. So I hope that gave you a little insight into all the different pieces that we set up from the beginning. And we are now having our first 2 enterprises spin out. We have an enterprise that's interested in tracking things globally with these new kinds of circuits. And then there's an integrated circuit company that is spinning out of Korea. And we hope that they can produce value in Singapore for years to come. Or, as we like to say, we're making silicon great again.